Right, let's look at the puppy running around the merry-go-round for a little bit longer before the next slide, which is not quite as interesting. So settle in, make sure you're signed in to Clicker, and that's the schedule for next week. Exam 2 on Wednesday. The coverage, if you guys have looked at the schedule, we're a little behind. So theoretically, I'm supposed to have Chapter 9 on this exam, but we haven't quite gotten there yet. So you don't have Chapter 9, you have Chapter 6, 7, and 8. The review session for this exam will be this Friday, 2 p.m. to 5 p.m., just like the last one. The location has changed. It's going to be in Olson 348. I'll send out another note about the review session with the equation sheet for the next exam. I'll post it in Blackboard tomorrow. Please study. This exam is a little bit harder than the last one. They get successively harder, but more fun. Same process, come at 7:30 and start early if you'd like. Same format. The exam is going to have different questions in the same format as you saw last time. And again, don't stress out. Start with the calculations if that makes it easier. Go to the concepts at the end. Okay. Right. This semester you also have to do a scientific writing assignment. This is 10% of your grade. Right? So 10% of your grade, to put it in perspective, makes it more important than a midterm. Right? All three midterms together are 25%. For this writing assignment, it's not really a physics writing assignment. I'm not asking you guys to write about physics. What I'm asking you guys to do is write about a perspective on physics. Right? Your perspective on physics located on two specific topics. Right? Women in physics and physics of energy in the modern world. The reason for picking women in physics is we're going to spend 2 semesters talking about Newton, Einstein, Maxwell. It's kind of lopsided. Physics historically is not very good at gender balance. And that's actually something you should check and test. Of all the physical sciences, physics lags behind. Even now, like we're at, I believe, 20% of PhDs are women. And that's something that, there are efforts in the world to change. It has to start earlier. But a lot of women have still done a lot of great physics, right? And I want you to recognize not just the physics, but their struggles in doing so, because a lot of this is historical. Okay? The other thing is, don't restrict yourselves to pure physics. Okay? Look and see if you can find applications in your fields. Okay? Like, for example, Rosalind Yalow, right, is a Nobel Prize laureate in medicine and physiology. She's a physicist. Okay, she came up with work that led to radioimmunoassays. Okay, Marie Curie is a double Nobel laureate, and she discovered radioactivity, which is used a heck of a lot in medical physics, in medical treatment and medical imaging. Okay, so put a perspective together which correlates their achievements to the modern world. Like, how are their achievements used? Okay, go beyond, oh, they studied here, they did this, and they got this and this prize. Okay, talk about the relevance. Is that making sense? Okay, it's not a technical article. The second topic is physics of energy in the modern world. We all hear about an energy crisis, and this semester you have at least started to understand at least what physics means when we talk about energy. Right? So in this topic, focus on energy solutions. You can focus on energy solutions in the developing world, energy solutions in the US, or the developed world. Also social awareness techniques. Basically, don't waste energy, right? Don't leave your lights on and stuff like that. But essentially, outreach, right? That is still part of energy education. Okay? So pick something, pick a technology, pick an area, pick a field, and put down your perspective on it. Okay? The style of the article is a magazine style. It's like something you'd read in a dentist's office. So it should be educational, but at the same time slightly entertaining. Do your own research. Wikipedia does not count as a valid citation. Okay? Look for the original sources. Right? You list the sources at the end. Read up. It's interesting as like a lot of the struggles and a lot that the technologies and the people involved went through make for great stories. Some of which are sad, but they're still great stories. Okay? Now, the first thing you have to do is talk to your recitation instructors, and within the first couple of weeks, submit a topic that they have to okay. Okay? So before you actually start writing your article, make sure your recitation instructor is on board with that article. Okay? The actual written assignment will be due on Blackboard. It's a safe assign assignment, which means it's checked for like plagiarism. But it'll be submitted on Blackboard. The due date is December 6th. That's before the final exam. It's about a week before the final, I believe. Or it's actually more than a week before the final. I think your final's on the 17th. But get this over and done with by then. No extensions. Okay. Now, those were the announcements. Let's get to stuff we actually have to cover for the next exam. This is where we were, where we left off, right? We're covering rotational quantities, and we've been going with translational analogs, right? Like, what is the translational quantity? What is the corresponding rotational quantity? We went all the way up from moment of inertia, which is what replaces mass, to kinetic energy, which is the rotational kinetic energy of an object, because a rotating object still has energy due to motion. Right? But we haven't talked about force. Okay, so if you guys remember, force in translational motion, right? Newton's second law, net force is equal to mass times acceleration. Right? So force is something that produces an acceleration. Right? When you apply a force on an object, you get an acceleration. When there's a net force, there's some A. Okay, so the next question becomes, at least as far as rotation is concerned, what do we mean by rotational force? Right? What kind of force causes rotation? Right? And it's actually not a force, it's an effective force, it's torque. Right? In order to produce rotation about some axis, right, you need torque. Which is the same thing as saying that in order to produce acceleration of some mass, I need a force. Okay? It's the same translational thing, just analogued into rotation. Right? Replace mass with inertia and replace force with torque. Right? So torques produce angular acceleration. Now, what is torque? So that little symbol there is tau. It's a little t in Greek, and that's the symbol we use for torque. Okay? Torque is defined as RF sine theta. Now let's understand what RF and theta are. R is the distance of the point of application of the force from the axis of rotation. F is, of course, the force applied, and theta is the angle between R and F. Right? So if I have some axis and I have some object, right, and I apply a force, right, then the angle between where the axis is to the point of application of the force and the force itself, in this case, is 90 degrees. Right? So theta in this case, which is the angle between that R and F, is 90. And sine 90 is 1. Right? So in this case, the torque is just R times F. In general, if I have some force applied at some random angle, right, the torque produced isn't quite that much. It's less than just R times F. It's RF sine theta. Right? So sine theta's maximum value is 1. So in this case, what you notice is as you start decreasing that angle, right? So change the angle of application such that now you're pushing along the axis of rotation. What should happen to the torque? Increase or decrease? It will decrease, right? Till you end up something like this where you can't produce torque. Everyone with me? right? Like if I apply a force like that about that axis of rotation, that thing is not going to rotate. Okay, let's cover that in a little more detail. The easiest way to think about this is just the simple act of opening a door, okay, which involves an angular acceleration, right? A door is an object that rotates about some hinge, correct? In order to get it to start rotating about that hinge, I need to apply a force which applies a torque. Everyone with me? We're going to do a small demo with Razvan. He's going to hold this, and he's going to be the axis of rotation, and I'm going to try and turn this, right? So, he's the axis without taking my eyes out, like that. Yeah. Okay, if I push, thank you. If I push this way, it turns, right? So I have applied a force, right, perpendicular to R, and I'm producing a torque. That makes sense? If on the other hand, now don't let it go down. Yeah. I push this way. I am pushing, right? Is it turning? No. So this would be equivalent to you going to the door and pushing it this way, trying to turn it. Right? You produce no torque. Correct? The other thing to notice is what happens, I'll keep holding it. If I push here, like where he's holding it, is it turning? Right? No matter what I do over here, it doesn't turn. That would be you going to a door trying to open it by pushing on the hinge. That makes sense? Doesn't work. Right? The reason it doesn't work is that at this point, if this is my point of application of force and this is the axis of rotation, I don't have any R. My R is 0. Right? R is the distance of the point of application of the force from the rotation point. If that distance goes to 0, I have no torque. Right? That's equivalent to pushing on the hinge. So that makes sense to everyone. Okay. So the reason doorknobs are not in the middle of the door, right, is to try and get as much R as possible. So you put the doorknob as far away from the hinge as you can, right, so that you need to apply less force to get torque. Does that make sense to everyone? You can increase torque in 3 different ways, right? Increase R, increase F, or get theta closer to 90. Right? Those are your 3 ways of increasing torque. Right? So doors are designed to essentially get you torque without too much application of force. Okay. Remember, torque is R times F times sine of the angle between them. For most wrenches and stuff, the angle is designed to be 90. Right? So you're applying a force which is at 90 degrees to the axis. So assume that in this question, theta is 90 and answer it. Got it? Oops. That way so you don't fall off. Right. Good. Just remember your units, right? SI units is still the same, force in newtons, length in meters. Right? So the units of torque will come out from that to be in Newton meters. Right, click something. Okay. this question is a little more interesting. Now, before you answer it, look at it. Right? Over here, this one is talking about axis of rotation 1, right? So this object has got 2 axes of rotation, which means the next question will ask about the second axis. Okay? But look at axis of rotation 1. Look at those 4 forces, F1, F2, F3, and F4, and rank them in terms of which one produces the least torque to the most torque. Does any of them produce 0 torque? That would be the lowest, right? Imagine this is the top-down view of you trying to open a door, right? And decide in which case would you be most successful and least successful in opening said door. So torque is RF sine theta. If you calculate torques for all of these, right? F1, the distance is R over 2, F is F, and theta is 90, right? So F1 is R over 2 times F. F2 produces R over 2F times sine of 45. F3 produces R times F, right? And F4 produces no torque, right? Because despite the fact, like if you look at F4, right? Despite the fact that R is long, point of application of the force is as far away as you can get from the hinge, right? It's parallel to R, right? So this is someone going and pulling on the edge of the door, trying to open it. Doesn't quite work. Pull hard enough, it will come off the hinges, but it's not going to rotate. That makes sense? Let's see. Yes, good. Right, so click the appropriate answer and then we'll move on to the next question. This one is asking you about the same 4 forces that you just did in your head to do it about axis 2 now. Again, the same things, right? If you're looking for the lowest amount of torque, the first thing you want to look for is, do any of them produce no torque? So now we're looking about axis 2. What is R for F3 and F4 about axis 2? 0, right? The lever arm is 0, right? The distance of the application of the force from the axis of rotation is 0, means you're pushing on a hinge, right? Not going to rotate. Everyone with me? We agree that F3 and F4 in this question about axis 2 produce no torque. Right? The question then becomes, which one produces more torque, F1 or F2? Right? F1 and F2 are applied at the same location, but F1 is applied at a 90-degree angle. Right? So that's your maximum torque. So that should be, yes, very good. Okay, click something. Right. It's very common, instead of talking about torque as RF sine theta, right, it's very common to talk about it in terms of what we call lever arms. Okay, a lever arm is nothing but the perpendicular distance from the axis of rotation to the line of application of the force. Okay, so I know that sounds like a bunch of words, but so let's say that this is my object, right, and this is my axis of rotation, and this is allowed to rotate in this direction. Right? If I apply a force here, right? The perpendicular distance from the line of action of the force. So extend this, that's the line of action of the force. Okay? The perpendicular distance to that is this guy. Right? This is perpendicular to the line of action of the force. Everyone with me so far? Right? We call this R perpendicular. Then the torque produced is just R perpendicular times F. Right? Which, by the way, if the angle between R, if this angle is theta, this is R F sine theta. Right? But that's the math part. The important part is look at what matters. It's how far this force is applied from the axis of rotation. Right? That is your lever arm. Right? So if I want more torque, I want a larger lever arm. This makes sense to everyone. Right? Increasing torque, keeping force the same, can be achieved by increasing the lever arm. Right? Which is nothing but the perpendicular distance from the line of action of the force to the axis of rotation. Right? We never want that to be 0. If that is 0, you don't get torque. But if you don't want it to rotate, you want it to be 0. But yeah. Okay. So that is all that this diagram is showing you. It's showing you lines of application of the force and the perpendicular distance to them. Right? That's what the third thing is. Right? Extend the line of application of the force, and the perpendicular distance from the axis of rotation is the lever arm. Right? For a given force, the longer the lever arm, the more the torque. Okay, that's what you want to take away from this. Everyone with me so far? Okay, directions on torque. So, let's say this is my object, right? If I have a force applying a certain torque, right, it's trying to rotate it, correct? I only have two options. It can either try and rotate it this way or this way, right? That's it. There's no other rotation possible, correct? So, remember pluses and minuses in translational motion were going left and right? Right? In rotational motion, the plus and minus is a clockwise and a counterclockwise. It's up to you to choose which is plus, then the opposite is negative. So if I have a torque that is trying to take this object this way, right? From my point of view, like that, right? That means it's trying to turn this object counterclockwise. That makes sense? So if I call that a positive torque, then some torque trying to do this is a negative torque because it's taking the object clockwise. Everyone with me so far? Right? So positives and negatives when it comes to what's a positive torque, what's a negative torque, that's up to you, but it's not based on left and right anymore. It's based on whether the torque is turning it clockwise or counterclockwise. Good so far? Okay. Right, so this is effects of increasing the lever arm, right? So you're trying to get the lever arm as far out as possible. This is the reason the doorknob is at the end, right? And of course, if the force passes through the axis of rotation, the lever arm is 0, right? If any force extended, like the line of action of the force is passing through the axis of rotation, there's no torque because the lever arm is 0. Right? The lever arm being the perpendicular distance from the axis of rotation to the line of action of the force. Okay, lever arms actually do come up a lot in anatomy because we are basically a bunch of levers. So, for example, eating, the masseter muscle, right? The point of, so the axis of rotation is the axis of the jaw, right? That's about which my lower jaw rotates, correct? The reason my lower jaw rotates, right? There's torque produced on the lower jaw. The reason that happens is I have a masseter muscle, which is not at the joint, right? It's some distance away from the joint. The further away it is from the joint, the reason it's so far down is so that you don't need to produce a lot of force to get enough crunch. Right? You want to be able to bite, right? The actual biting is torque, correct? that torque is produced because that muscle applies a force at a certain distance from the axis of rotation. Everyone with me so far? Right? The same thing is true of your forearm, right? So like your forearm, you have two muscles. One of which is attached at the elbow joint pretty much, right? Which is at your axis of rotation, right? So right there. The other one pulls, right? So the further away this second muscle is attached, the more torque I will get, right? Humans, it's actually pretty close, right? Those two muscles are attached pretty close. So that means that your lever arm is pretty short, right? So while they're capable of producing a lot of force, they're not capable of producing a lot of torque, right? Like one of the few differences between us and chimpanzees is the location of where that second muscle is attached, right? In a chimp, it's attached further away from the elbow, right? Which means that despite the fact that they have smaller forearm muscles, right, they're actually capable of generating more torque, right? They have a significantly longer lever arm, right? So chimpanzees can get a little more torque than I can. I was kidding about few differences. There are multiple differences between me and a chimpanzee. They have more hair. Okay. So this is our story so far. We have torque, which is what replaces force, right? So just like force causes acceleration, torque should be causing angular acceleration. And that is Newton's second law for rotational motion. It is literally F equals mn, right? For rotation, F is replaced by tau, torque, m is replaced by I, the inertia of that system about that axis, right? And A is replaced by alpha, an angular acceleration, right? So torques produce angular accelerations. So, the summary of all of this is ways to close the door more quickly. Push harder is increasing F. Push further away is increasing R perpendicular. Push perpendicular to the hinge is getting sine theta to its max value. Right? Those are the three things, the only three things torque will depend on. Right? Distance of application of the force from the axis of rotation, the amount of force applied, and the angle between those two. Okay. I haven't opened the question yet because we're going to need to do a little bit of math for this. This is a relatively simple problem, right? Well, it's a common situation. I'm guessing most people sat on a seesaw at some point in their lives. Okay, so in this case, it's not a full-on seesaw. It's just two kids trying to balance themselves on what's essentially a balance, right? Now, in order for this thing not to rotate, what must be true? Remember, if there is a torque on the system, right, if the net torque on the system is non-zero, there will be angular acceleration, right? Just like saying if there is a net force on a system, there is acceleration, right? If there is net torque on a system, there is angular acceleration, right? So if this thing is not supposed to be rotating, right, the net torque on this system must be zero, right? And the net torque on this system must be zero about any axis, right? Because if there existed an axis on this system about which the net torque was not zero, it would rotate about that axis. Does that make sense? Right? So our condition for this thing to be at rest is that the total sum of torques acting on it needs to be zero. Everyone with me so far? Okay, now the reason I didn't actually open this question is we have to set it up mathematically before we can solve it. Right, so as before, my first step is draw a diagram. Okay, one big difference about these diagrams, it's going to be a free body diagram, right? So I'm going to list the forces acting on the object, but I also have to list where they act. Right? Unlike Newton's laws, where I'm just interested in the total force acting on the object, right, and the directions of those, and then I get a vector sum. Right? Over here, it's not just a question of which forces are acting on the object. It matters where the forces are acting. Right? Because we're looking at torques. It's R and F. Right? So in my diagram, I need to be sure that I'm putting R's down. I need to know those distances. Is this making sense? Right? So it's not just a question of which forces. You want to make sure you also put down the distances. Right? So this thing is touching that pivot point here. So there is a normal force on it from that pivot point. It has its weight downwards, mg, right? So that's this thing's weight downwards. It's a block, it has weight. You have one kid who has a mass of 30 kgs, that's ma. So that's this guy sitting here. He, of course, has weight. Right? So his weight is pushing down on the block. Okay? So this is his weight on the block, and he is sitting at a distance of 2.5 meters from the pivot. Everyone with me so far? Right? Since he's sitting 2.5 meters from the pivot point, his weight is a force acting on the block 2.5 meters away from the pivot point. Right? Similarly, for position B, so I have MB, that's the mass of child B, is 25 kgs. Right? And that distance is x. Right? This is what we need to find. How far does person B need to sit to balance this system so that there is no torque, so it doesn't rotate? Right? Okay, those are the forces acting on this system. Right? The next question becomes, pick an axis of rotation. Before we can start calculating torques, we need to know where to measure R from. Right? The nice thing about this setup is it's supposed to be at rest. Right? So which means that I can pick any axis I want, and the torque about that axis must be 0. Right? Since it isn't rotating about anything, I can pick any position on that board and it's not rotating about it, so the torque about that point is 0. Okay? Which frees you up to do a lot of nice, cool stuff, as in you can neglect some stuff. If I pick this, right, the center of my board as my pivot point, right, then mg, the weight of the board, is at that point. So it produces no torque. Right? The normal force is at that point. It produces no torque. Does that make sense? If I'm picking this as my axis of rotation, this force and this force produce 0 torque. Right? They're acting at the point of rotation. So R is 0. Correct? The other two forces do produce torque. And before we list them, we need to decide on a direction as positive and negative, because one will produce a positive torque, the other will produce a negative torque. Okay? So again, sign conventions. And this question actually gives you a sign convention. Right? If you look at the edges, you're told that a clockwise torque in this question is a negative torque. Right? And a counterclockwise torque in this question is a positive torque. Everyone with me so far? Okay. Now let's start calculating the torques. Right? So we have that this way, right? Turning towards A is positive. Okay, so my equation, of course, is net torque, right, must be 0. Right? The sum of all the torques acting on this system must be 0 because it's at rest. Okay, so this is the torque produced due to kid A, plus the torque produced due to kid B, plus the torque produced due to the seesaw itself, plus the torque produced due to the normal force. All of these must add up to 0. Right? Since I've picked this as my axis of rotation, this guy is 0 and this guy is 0. I'm left with tau A and tau B. Right? Tau is R, F sine theta in general. So tau A, right, that means the torque produced by this force about this point, R is 2.5 meters. F is the applied force, that's ma times g. And theta is the angle between these two, that's a 90. So it's sine of 90, which is 1, right? So tau A comes out to be 2.5 times ma times g. Right? I know ma and g. Like ma is 30 kgs and g is 9.8. And this is a positive torque, right? It's trying to turn the object this way, in my positive direction. Okay? Similarly, do the same thing for tau b. Tau b is a distance x away from the axis of rotation. This is what I'm trying to find, right? So put x. The value of the force, the magnitude of the force applied is now mbg, right? The weight of the second kid. Right? And sine of the angle between them, which again is 90. Right? So tau b comes out to be minus mbg times x. And it's a negative torque because it's trying to turn it in the other direction. Right? Because I've said this way is positive, so a torque trying to take it the other way would be negative. Right? Now add them. Right? So this plus this, tau A plus tau B is 2.5 mag minus mbg times x equals 0. Right? Everyone with me so far? The torques, so this and this, the torques produced due to the normal force and the weight of the board, about this point. These are forces, right? The normal force is acting on the board, correct? So it might produce a torque. So I need to account for it, right? But it's at the point of axis, it's at the axis of rotation, so it doesn't produce a torque. So that torque is 0. Because we're looking at why the board doesn't rotate, right? So a free body diagram is the forces acting on the object, right? I'm not doing a free body diagram of the kids. I'm doing a free body diagram of the board, right? The normal force from the board acts on the kids. That's not a force acting on the board. The weight of the kids is a force acting on the board, okay? Right, so end up solving that equation. And that's the answer to that question. Fun, right? It comes with practice. And what you'll find, of course, is something you know from intuition, that the heavier kid, right, and I mean that in a nice way, the heavier kid needs to sit closer to the axis of rotation for this thing to balance, right? So that the heavier kid produces less torque. Right? If they're both sitting equally far away, the heavier kid will produce more torque. Right? That thing will rotate. Right? So logically, the heavier kid needs to move in. Right? Anyone who's used a weighing balance has done this. What is the? It's 0, right? It's R, F, sine theta. So F is non-zero. It could be n or the weight of the board. But both of them act at the axis of rotation. So R for that force is 0. So what is what?
What does it represent?
The torque. Right? It's talking about the torque produced by mg about that point. Okay, I'm now going to open the question so you guys can actually answer it. And then we will do a quick demo. Oh, very good. Right, click something. Okay, I'm closing it. Good. So when you solve it, you'll get 3 meters. Right, one last quick topic, and that's angular momentum. So just like there is a linear momentum, which is a measure of the amount of motion in the system, there is an angular momentum, which is a measure of the amount of rotation in the system. We define torque as RF. We define momentum as R times P, where P is the linear momentum, right, mv. Another way to define it is, if you remember, we defined momentum P as m times v, right? Now we're in rotation. If we're talking about angular momentum, replace m with the moment of inertia I, replace v with the angular speed omega, right? So the angular momentum becomes I omega. Another math form for it is just mv times r, because P is mv. Okay, so if I have an object rotating about some axis, and that object has an inertia I, right, its angular momentum is I times omega. If I have some particle of mass m moving with a speed v in some radial r, its angular momentum is mvr. Right? So those two equations, the difference is one applies to like an object which has an inertia, the other applies to a point particle. They're equivalent. Okay. If you guys remember, conservation of momentum, right, was that the total momentum of a system is conserved in the absence of an external force. Right? So remember collisions. We defined the objects, everything colliding as part of my system, simply so that I had no external force and I could conserve momentum. Right? Didn't matter if it was elastic or inelastic. Right? The analog, the direct analog for that becomes, in the absence of external torques, right, the angular momentum of the system must be conserved. Everyone with me so far? And this is something, I mean, mathematically it's one thing, but it's something you actually see a lot. And you're going to see it with Razvan in one quick second. Right, so he's going to sit on top so that everyone can see. And he's going to spin on the stool and presumably no one gets hurt. I did promise I'd have a spinning person on the desk. Right, he's going to start spinning and then he's going to draw in his arms and legs. So he's going to start spinning with his arms and legs out. But before he does any of this, you're going to tell me what happens when he moves his arms in. So he's going to be spinning like that out first. Okay, like I'll help him start spinning. Once he's spinning, he's going to do this. Right? He's just moving his arms inwards. What is he changing? Is his mass changing? So the distribution of the mass is changing, correct? And how is it changing? Is it coming closer to the axis of rotation or going further away? It's coming closer, correct? So it's decreasing, right? Remember, as the mass gets closer to the axis of rotation, rotational inertia decreases, right? So if his rotational inertia decreases, what should happen to his angular speed and y? Increase, because angular momentum is conserved, right? I times omega must stay constant, right? So if I decreases, omega must increase as long as there is no external torque on it. That makes sense to everyone? Okay, so I'm going to open the question and then start spinning him. Right. Arms out. Okay, his arms went in. Now he's going to take his arms in. Not quite that dramatic, but okay, he did speed up. He stopped himself. Are we good so far? Did everyone actually see him speed up and get a little scared? You okay? You okay? Okay, he's well and good. So answer the question and then you have to let go for around 500 people to come in. Very good. They spin faster, and now he's just spinning. Right, that's it. There's an exam coming in, so I will see you guys at the review session. Did I spin you very fast? What's up, Brendan?
So are we ever going to learn about like the angle of an object that's rotating?
What do you mean the angle?
Like does an angle change? Like when it's on an angle rotating, does it change at all the speed or no? Because it looked like he was like leaning in, sort of. So
Moving
when he was speeding up.
Yeah, he didn't move in. His arms did.
No, I know. When he was moving in, it looked like his chair was leaning over.
That's because his weight was changing. That had nothing to do with
Okay.
his rotation. It's just got to do with
So when
he was a little unsteady.
Right.
So he was moving.
So
But
when
if he
it's,
stayed steady, like a figure skater, holding their arms in, they speed up.
so if it was at an angle, would that change the motion? Or just stay the same?
Angular momentum will stay conserved.
Okay. At any given angle.
At any given angle, angular momentum will be conserved.
Like that Ferris
You have to
wheel.
be in the absence of external torque, so you have to be careful.
Okay.
There's no torque outside.
Gravity is an external force?
Gravity is an external force.
Yes.
Where it acts depends on whether or not there's a torque.
Okay. Where it acts.
Right, because if it's acting at the center of the object, right, and the axis of rotation is the center of the object, gravity produces no torque.
Right.
So, like for him, I mean, he obviously had weight, but that's not an external torque on him because it's at the axis of rotation.
And it's him pushing himself instead of the gravity pushing, rotating.
Gravity has nothing to do with his weight.
Yeah.
Right, it has no torque.
It's just him.
So it's not an external torque. So that's why his momentum is good. Right? It wouldn't work for linear because it's a force, and so momentum can't be conserved in an external
It
force.
won't be, yeah. All right. Thank you.
I'm rushing to sorority this semester.
Sorry?
I'm rushing to sorority.
Okay.
To do progress reports like once or twice in the semester just to say we're keeping up with things. So I just need you to look over this and sign it. There's a sheet that you're smoking in.
I can't. Oh, can I?
Up here. Feeling social.
Okay.
I didn't know if there's anything else to
Is it me? No, it's not Monday, Wednesday, Friday. Lectures on Friday.
Wait, Monday, Wednesday.
Also,
Sorry, I didn't even...
shouldn't your recitation instructor sign this since they would know about your assignments and stuff like that?
I have recitation as
Oh,
another
that's separate?
section in there. Yeah. Sorry,
That's
I'll
fine.
erase the Monday, I mean the Friday part. Yeah. Sorry. Just trying to do the hardest. Alright, thank you so much.
You're welcome.
See you not on Friday.
Yeah.